Good morning, everyone. So, today here we'll start with the next module, module 5. So, in this module 5, we'll discuss determinants, eigenvalues, and eigenvectors. So, here the first part it deals with the determinants, where we can discuss the properties of determinants, permutation, and cofactor, and the related problems on the determinants. And in the second part, so we have eigenvalues and eigenvectors. So where we can go through the review of eigenvalues, diagonalization of matrix, special matrices, which includes positive, definite, and symmetric matrices, and their properties, and singular value decomposition. And on all this, we are going to solve the problems. So here, hope all of you have written the test well. ಚೆನ್ನಾಗಿ ಮಾಡಿದ್ದೀರಾ ಟೆಸ್ಟ್? ಟೆಸ್ಟ್ ಹೇಗೆ ಮಾಡಿದ್ರಿ? ಈಸಿ ಇತ್ತಾ? Anyone can reply me back. Chandana? Chandana GP. Can you hear?
Yes, ma'am.
How you have done the test?
Good, ma'am.
Okay. So you are able to solve most of the problems, right?
Yes,
So
ma'am.
here this semester probably we are having the open choice question type of exam. So open choice
Yes.
means, so here it is a theoretical, that is you need to write the exam offline only. So you will be given the 10 questions. So out of 10 questions, you have to answer any 5. So here previously what we were doing, so here from each module we were giving 2 questions and you have to select at least one question from each module and you are answering 5 questions, right? But this semester, so 10 questions, so 2 questions from each module, but you can answer any 5 questions without any restriction. You can answer complete 2 questions from the module 1 itself. Similarly, you can select the questions, complete questions from the module 2 and module 3 and so on. So here like that, you can select any 5 questions out of 10 and you can answer. So this time, so we have a better option. So you can go through the topics, whatever I have covered. So here you can concentrate on module 1, module 2, module 4 and module 5, whatever I am doing now. So here for passing as well as scoring, so these topics, it will be helpful. So can you understood whatever I told? Understood?
Yes, ma'am.
ಸೊ ಓಪನ್ ಚಾಯ್ಸ್ ಇರುತ್ತೆ. ಓಪನ್ ಚಾಯ್ಸ್ ಅಂದರೆ 10 ಕ್ವಶನ್ಸ್ ಕೊಡ್ತಾರೆ. ಸೊ ಯು ಹ್ಯಾವ್ ಟು ಆನ್ಸರ್ ಎನಿ 5 ಫುಲ್ ಕ್ವಶನ್ಸ್. ಸೊ ನೋ ರಿಸ್ಟ್ರಿಕ್ಷನ್. ಸೊ ಯು ಕ್ಯಾನ್ ಸೆಲೆಕ್ಟ್ ದ ಕಂಪ್ಲೀಟ್ ಕ್ವಶನ್ಸ್ ಫ್ರಮ್ ಅ ಸಿಂಗಲ್ ಮಾಡ್ಯೂಲ್ ಇಟ್ ಸೆಲ್ಫ್. ಸೊ 2 ಕ್ವಶನ್ಸ್ ಕೊಟ್ಟಿದ್ರೆ 2 ಕ್ವಶನ್ಸ್ ಮಾಡ್ಯೂಲ್ 1 ಇಂದ ಬಂದಿರುತ್ತೆ. ಸೊ ಕಂಪ್ಲೀಟ್ 2 ಕ್ವಶನ್ಸ್ ಯು ಕ್ಯಾನ್ ಆನ್ಸರ್. ಸೊ ನೋ ರಿಸ್ಟ್ರಿಕ್ಷನ್, ಒಂದೇ ಆನ್ಸರ್ ಮಾಡಬೇಕು ಅಂತ ಏನಿಲ್ಲ. ಸೊ ಇಟ್ ಈಸ್ ಅ ಬೆಟರ್ ಆಪ್ಷನ್ ಫಾರ್ ಯು ಪೀಪಲ್. ಸೊ ಹ್ಯಾವಿಂಗ್ ದಟ್ ಇನ್ ಮೈಂಡ್, ಯು ಕ್ಯಾನ್ ಕಾನ್ಸಂಟ್ರೇಟ್ ಆನ್ 3 or 4 modules. 4 modules is enough, I think. So instead of concentrating only on 3 modules, you can concentrate on 4 modules and you can prepare well. So here now coming back to this, so here we are going to discuss about the module 5. So where determinants is the first topic. So here in order to start with the determinants, first let us go with the basic definition of determinant. So your determinant is nothing but, as you know, it is a single value. So when you solve, so you are going to get a single value. So using that single value, you can, or you will be able to analyze so many things. So here this determinant, it is usually used in order to solve the linear equations. So and also it can be used in order to compute the multi-dimensional integrals. That is, whenever whatever the integrals that we used to solve with the help of change of variables. So in order to solve such integrals, this determinant will be helpful. And also it is useful for understanding the cross product in physics or mechanics. That is, as we know, we have interdisciplinary. So in many of the interdisciplinary engineering concepts, you can make use of this determinant. So now in today's class, we'll just discuss the determinant uses and we'll try to cover, completely try to cover the properties of the determinant. So now Coming to the determinant, as I told, it is nothing but a single value. So how we are going to calculate this? So this determinant value, it is going to be calculated by the method of elimination. So that is nothing but you are going to apply the row echelon method, whatever we have studied in the module 4. So you are using that concept, elimination method, we will be able to get the value of the determinant. And also this determinant, it provides an explicit formula for each entry of A inverse and A inverse B. So as I told, so this determinant, it is going to result in a single number value which is obtained after the elimination, and it can be used to analyze the various concepts about that particular matrix. So now coming to the uses of determinants. So here we can have four main uses of determinant. So the first use of the determinant, so it can be used to test for the invertibility of a matrix. So whenever you'll be given a matrix, so matrix A kotirtare, so you have to identify whether that matrix A is invertible or not. Suppose when you simplify the determinant of the matrix A, and if that matrix A determinant it results in 0, then we can say that that matrix A is not invertible. So determinant ಏನಾದ್ರು 0 ಬಂತು ಅಂದ್ರೆ, so that is non-invertible. In other words, you can say that such matrix is a singular. So singular in the sense you will not be able to degenerate the matrix. So ಮತ್ತೆ matrix ಅನ್ನ reconstruct ಮಾಡಲಿಕ್ಕೆ, regenerate ಮಾಡಲಿಕ್ಕೆ ಬರಲ್ಲ. So here in such cases, so in order to test the invertibility of a matrix, you can use the determinant. So here, if the determinant of the matrix A is 0, then we can say that such matrix A is a singular, and or you can also say that it is a non-invertible. So suppose if the determinant of A is not equal to 0, suppose if it is not equal to 0, ಯಾವುದೋ ಒಂದು constant value 1 ಬಂತು 2 ಬಂತು, so whatever may be the value, then we can say that that matrix A, it is invertible. That is invertible in the sense we can regenerate the matrix A. So here we can write A inverse is equal to 1 divided by determinant of matrix A. And here, whatever the invertibility property we have, so it is very important to the family of matrices which is defined by the form A minus lambda I. So lambda is nothing but some constant. So here this lambda, it is going to be subtracted all along the main diagonal. So here you can see that lambda it is multiplied with I. So here I is nothing but a identity matrix. So as we know, in the identity matrix, all the diagonal elements will be 1. So when you multiply lambda with I, so here all the diagonal elements will be having the value 1. And the other elements in the matrix, it will be 0. So here all the diagonal element, it is going to be subtracted from the elements of the matrix A. And it will help in finding the eigenvalue for which A minus lambda I is going to be a singular. So here when you come to the eigenvalue, so here this is going to be covered in the next part of this model. So here eigenvalue, I'll just tell what it is. So it is nothing but a scalar which is associated with the given linear transformation of a vector space, and it will be having the property such that there is some non-zero vector which when multiplied by the scalar, it will be equal to the vector obtained by letting the transformation to operate on the vector especially. So that is nothing but you just assume it is a scalar value. So we'll see how to calculate eigenvalues and so on. So now for this equation A minus lambda I, so for this we are going to calculate the determinant, and suppose if the determinant of this is equal to 0, then we can say that it is a singular. So here A minus lambda I determinant value singular means, so here it will be useful in finding the eigenvalue. So all these properties you need to remember. So whenever you will be calculating the eigenvalues, so then you should remember that the determinant of such equation A minus lambda I, it must be equal to 0. So when you say 0, it is a singular. So suppose if the given matrix is singular, then you can calculate the eigenvalue. And here this equation, it will be having n roots as well as n eigenvalues. We'll see how to calculate all those in the upcoming classes. So now the second use of the determinant. So here the second use of the determinant is the determinant of the matrix A, it is equal to the volume of a box in the n-dimensional space. So you can take either one dimensional or two dimensional or three dimensional or four dimensional or n dimensional space in general. So here, when you calculate the determinant of a matrix A, it is simply equal to the volume of a box which is defined in the n dimensional space. So here you can see this diagram. So here we have x, y, z. So when we have three coordinates x, y, z, so it is nothing but a three-dimensional space. So in this, we are going to define some box. So here it is with a coordinate like here you can see that it is provided with the coordinate a11, a12, a13. Similarly, here a21, a22, a23, a31, a32, a33 and so on. So now whatever the edges, so these are called as the edges. So edges is nothing but the point where one or more lines they are going to intersect at a particular point, right? So here the edges of the box, they come from the rows of the matrix A. So that is A11, A12. So these values, they will be used to define the edges of the box. And here, suppose if we consider a matrix A, so in that, so here we'll be having various elements which is distributed in rows. So when you have rows, obviously you will be having the columns. So here the columns of such matrix A, it would give an entirely different box with the same volume. So volume same irutte, but the shape of the box it will be different because of the different values in the coordinate. And here, in such case, so here the small box in a little cube, it can be defined by the differential volume. So here we use the term differential volume. So differential volume in the sense, so here we'll be having small changes in the coordinate values x, y, z. So here for example, if we have the coordinate a21, a22, a23. So this a21, it may be defining x coordinate, a22, it may be defining y coordinate, a23, it may be defining z coordinate. Suppose if we increase each of these coordinate by a small amount, so 0.1, 0.1, 0.1 in the increment madre. So originally if you assume the coordinates as 1, 2, 3, so the new values will be 1.1, 2.1, 3.1. So that will be defining a new volume. So here in such case, the differential volume, it is simply equal to the product of the differential change in the coordinate, that is dx into dy into dz. So using this equation, we can also obtain the volume of a box, total volume of a box, just by taking the triple integration over this dx dy dz. That is v is equal to triple integration f of x comma y comma z into dv. So where f of x comma y comma z is nothing but some function. So that will be defined. And here in order to as I told, this determinant, it is equal to, it is used to define the volume of a box. So in order to arrive at that point, so here we can make use of the cylindrical coordinate, because when you say the box and if you imagine in a space, it looks like a cylinder. So here in order to simplify that, we go with the cylindrical coordinate. So when you come to the coordinate, actually here we have various types of the coordinate system. So the first one, we can take the simple one, that is the rectangular coordinate system, which is also called as the Cartesian coordinate system. The second one is the cylindrical coordinate system. Third one is the spherical coordinate system. So these are the main three coordinates usually which is used by most of the engineers in order to analyze the system. So here, as I told, the first one is the rectangular or the Cartesian. So in order to define the system in a rectangular coordinate system, so here we need three coordinates x, y, z. And similarly, when you come to the cylindrical coordinate, in order to define a system in a cylindrical coordinate system, so here also we require three coordinates which are taken as r, theta, z. And similarly, when you come to the spherical coordinate, so the coordinates required are r, phi, theta, r, theta, phi. So ಮೂರು coordinate system use ಮಾಡ್ತೀವಿ. One is the rectangular, second one is the cylindrical, third one is the spherical. So ನಿಮಗೆ ಯೂಶಲಿ ಎಲ್ಲ ಸಿಸ್ಟಮ್ ಏನಿರುತ್ತೆ ರೆಕ್ಟ್ಯಾಂಗ್ಯುಲರ್ ಸಿಸ್ಟಮ್ ಅಲ್ಲಿ ಇರುತ್ತೆ. ರೆಕ್ಟ್ಯಾಂಗ್ಯುಲರ್ ಸಿಸ್ಟಮ್ ಅಂದ್ರೆ 3 coordinates will be there, that is x, y, z, as you can see here. And when you come to the cylindrical coordinate, so it will be defined in terms of r, phi, z. Or you can also say r, theta, z. Here we have taken theta, so usually it will be given in terms of phi. And the spherical, so r, theta, phi coordinates will be used. So now restricting this topic to the cylindrical coordinate. So here Initially, all the system they will be given in the Cartesian coordinate system, which are defined in terms of x, y, z. And these x, y, z, they can be transformed into the cylindrical coordinate using the equations x is equal to r cos theta, y is equal to r sin theta, z is equal to z. ಸೊ ಎಕ್ಸ್ ಕೊಟ್ಟು ನಿಮಗೆ ಟೀಟಾ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ಅಥವಾ ಟೀಟಾ ಕೊಟ್ಟು ಎಕ್ಸ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ವೈಸ್ ಎವಾಸ ಯು ಕ್ಯಾನ್ ಯೂಸ್. ಸೊ ಎಕ್ಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಆರ್ ಕಾಸ್ ಥೀಟಾ, ವೈ ಇಸ್ ಈಕ್ವಲ್ ಟು ಆರ್ ಸೈನ್ ಥೀಟಾ, ಝೆಡ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಝೆಡ್. So now when this dx, if it is stretched to the point dx by du into du, then this u it is going to replace the x using the volume equation, so which will be resulting in the value j dr d theta dz. So this j it is called as the Jacobian determinant. So here we may ask to calculate this Jacobian determinant, which is a three-dimensional analogous for the stretching factor dx by du. So now considering this Jacobian factor, so here we can write the Jacobian matrix as dou x by dou r, dou x by dou theta, dou x by dou z. So as I told, so here the Cartesian coordinate values x, y, z. So they have to be expressed in terms of r, theta, z. So here in the second row, so here we have dou y by dou r, dou y by dou theta, dou y by dou z. And similarly in the third row, we have dou z by dou r, dou z by dou theta, dou z by dou z. So when you ask to calculate the Jacobian matrix, so in that case, so we need to make use of the equation x is equal to r cos theta in the first row, that x is equal to r cos theta in each and every column, it has to be differentiated with respect to r theta z. Similarly, when you consider the second row, so here we'll be having y is equal to r sin theta as it is defined here. And in the third row, we'll be taking z is equal to z and we'll be differentiating with respect to r theta z. So now, writing this Jacobian matrix, so now you can differentiate x with respect to r in the first element dou x by dou r. So now we differentiate madadre what we get, so it will be resulting in, so r cos theta differentiation with respect to r is cos theta. So differentiation of r is 1 with respect to r. Similarly dou x by dou theta, so here we will be differentiating with respect to theta, so r will be there, and differentiation of cos theta is minus sin theta. And dou x by dou z, so here since it is independent of z, so here it will be resulting in the value 0. Similarly, when you consider the second row, so here we need to differentiate y with respect to r, theta, z. So here the differentiation of r sin theta with respect to r is sin theta, and the differentiation of r sin theta with respect to theta is r cos theta, and with respect to z is 0. Similarly, in the third row, it will be resulting in the value 0, 0, 1. So now for this, if you calculate the determinant, so here the determinant it can be obtained like this. So here j is equal to, so here cos theta, so here leaving this first column, first row, so you can get the cofactor, that will see what is that. So r cos theta into 1 minus 0, so plus, that is minus of minus r sin theta is nothing but plus r sin theta. So leaving the first row and the second column, so here it will be resulting in sin theta, and similarly plus 0. So simplifying this, here you can see that, so here we have obtained r cos square theta plus r sin square theta. Since r is common in both the side, so here we can take r as a common within the bracket cos square theta plus sin square theta. But cos square theta plus sin square theta, as we know, the sum of these two, it is equal to 1. So here we will be getting the Jacobian value as r for the cylindrical coordinate system. So this r is nothing but the radius of the cylinder. So now using this, the volume of the cylindrical element, which is taken as j dr d theta dz, which is defined here. So here in this place, we are going to substitute j as r. So here the volume, it is equal to r dr d theta dz. So here the second use of the determinant is the determinant of the matrix A. It is simply equal to the volume of a box in the n-dimensional space. So that is r dr d theta dz. And now coming to the third use. So here the determinant, it can be used to or it can be used as a formula for each pivot. So here theoretically, suppose if we consider a pivot entry is 0, it requires a row exchange. So nimage first starting let pivot entry, pivot is nothing but a non-zero element. So suppose if the pivot entry is 0, then we are going to make use of the row exchange. So this will be seeing with the help of an example. So here from the formula, so here we can write that determinant, it is equal to the product of the pivots with plus or minus sign. So here determinant, so it is simply equal to the product of the pivots. And it follows that the regardless of the order of elimination, the product of the pivot, it is going to remain the same apart from the sign. So either you may get plus or minus, it doesn't matter. But here, even after the elimination, the product, it is a product of the pivot, it is going to give the same value. That is the third use. And the fourth use, the determinant, it can be used to measure the dependence of A inverse B on each element of B. So if suppose if one parameter is changed in an experiment and an observation is corrected, then the coefficient in A inverse, it can be taken as the ratio of the determinant. So this property or this use also we can observe while solving the problem. And here, the next one is that we are going to discuss about the properties of the determinants. So before discussing the properties of the determinant, so first here we'll see, so the determinant, it can be defined by the three most basic properties. So here the first one is the determinant of the identity matrix, always it will be equal to 1, and the sign is reversed by a row exchange. So each time you exchange the row, the sign is going to be changed. Suppose if we exchange the row once, so suppose if the plus sign is there, that is going to be changed to minus sign. And similarly, if you are exchanging the row for 2 times, then again the sign is going to be changed. That is plus to minus, minus to plus. And also the third one is the determinant, it is linear in each row separately. So having these three properties in our mind, so here we are going to discuss totally I think 10 properties are there. So the most basic property is that determinant of the identity matrix, it is always equal to 1, and the sign is going to be reversed for each row exchange, and the determinant is linear in each row. So having those concepts in our mind, so here first we are going to look at the various properties of the determinant. So now, before considering the properties one by one, so here let us consider the matrix with the elements A, B, C, D. So for which if you ask to calculate the determinant, it can be obtained as determinant of A, B, C, D, which is nothing but AD minus BC. That is cross multiplication AD minus BC. So this possesses every properties, and every property it can be considered as a consequence of the first three properties. And also the rules can be applied to the square matrices of any size. So here let us come to the properties one by one. So the determinant of the identity matrix, as I told, always it will be equal to 1. That is, you can write determinant I is equal to 1. So here, for example, we can consider 2 cross 2 matrix, 2 cross 2 identity matrix. Identity matrix in the sense the diagonal elements will be 1 while the other elements will be 0. So here, when you consider such 2 cross 2 identity matrix, here you can see that 1 into 1 minus 0, that will be resulting in the value 1. So now you can also consider 3 cross 3 identity matrix. So here all the diagonal elements are 1, excluding the other elements which will be 0. So here also, if you consider, if you solve this determinant, it will be resulting in the value 1. So you can consider the square matrix of any order, so for which the determinant of the identity matrix, always it will be resulting in the value 1. So this is the first property. And next, the second property is the determinant, it changes the sign when 2 rows are exchanged. So here, for example, here we have the original matrix as A, B, C, D. So for which we have obtained the determinant value as AD minus BC, right? So now, if we exchange these 2 rows, that is the second row, it will be transferred to the first row elements will be shifted to the second row. So if you do that, here you can see that we have determinant of CD, AB. So when you solve this, so here the determinant, it will be giving the value BC minus AD. So which is equal to minus of AD minus BC. So here which is expressed in terms of the determinant as minus of ABCD. That is, as I told, the determinant is going to change its sign when 2 rows are exchanged. And now, if you consider the determinant of every permutation matrix, so the determinant of such permutation matrix, it will be either equal to plus or minus 1. So what do you mean by permutation matrix? Permutation matrix is nothing but a binary matrix. So binary in the sense it will be having the values 1 or 0. So it might not be the identity matrix. So but it is a permutation matrix with zeros and ones. Only zeros and ones irutte. So in this permutation matrix, it can also be transformed to the identity matrix when you go for the row exchange. So row exchange operation madi. So permutation matrix, it can be converted to the identity matrix. So identity matrix is different from permutation matrix, that you have to keep in our mind. So identity matrix also consists of zeros and ones, but ones always it will be present in the diagonal places in the case of the identity matrix. But when you come to the permutation matrix, the zeros and ones, it may be present anywhere. Anywhere you may have zeros and ones, but with the help of row exchange operation, that permutation matrix, it can be converted to the identity matrix. And here the determinant of such permutation matrix, always it will be equal to either plus 1 or minus 1. And next, here each row exchange, as I told, it will be resulting in the switching of the sign until we reach the determinant of I is equal to 1. That is the second property. And the third property is the determinant, it depends linearly on the first row. Suppose if we consider the three matrices A, B, C, and they are the same from the second row down. So in the sense, for example, I'll just take up with the notebook. I'll just go with the notebook here. Can you see the screen here? If you have any doubt, if you're not understanding, you can stop me at any time and you can ask. Can you see the screen?
Yes, ma'am.
Are you listening? Are you understanding whatever I'm telling? If you don't understand, you
Yes,
can
ma'am.
no problem.
Yes, ma'am.
Okay. So here we will be given three matrices A, B, C. So here we will be having some elements for each of the matrix. So from the first row elements, leave it. From the second row onwards, these matrices, they will be same. So here we are going to consider three matrices A, B, C. They are the same from the second row onwards, and row 1 of the matrix A, it is nothing but the linear combination of first rows of the matrix B and C. So second row in the ಎಲ್ಲ elements same ಇರುತ್ತೆ A, B, C ಅಲ್ಲಿ. But when you come to the first row, so first row of the matrix A, it is equal to the linear combination of the matrix B and the matrix C. So this linear combination, so whatever we'll be using for B and C, it is going to involve two operations. One is the adding vectors, and the second one is it will be involving the multiplication by the scalars. So these two properties, it will be involved while generating the linear combination for B and C. So now we are going to consider the matrix B. So let us assume B is defined as A, B, C, D, and C is defined by A dash, B dash. The second row elements, it should be same as that of the B. So even A du kuda second row elements, it will be same as that of CD. That is B and C. So now having this, so now we have to write determinant of the matrix A. So determinant of the matrix A, so it is equal to A plus A dash, B plus B dash, and the second row elements will be same. So here will, as I told, the first row elements of the matrix A, it is obtained by the linear combination of the first rows of the B and C. So here we have A, B and A dash, B dash as the elements of the first rows of B and C. So here by considering the adding vectors rule, so here we can write the first row element for the matrix A as A plus A dash, B plus B dash, and the second row elements will remain same, C and D. So now, so having this determinant A is equal to this much. So now if you multiply the row 1 by T, uh, sorry. So now if you simplify this, here you can see that if you solve the determinant, it will be resulting in D into A plus A dash minus C into B plus B dash. So which will be equal to, so here you can see this is equal to AD plus A dash D minus BC minus B dash C. So this is the equation for the determinant E. So now considering B and C, B is A, B, C, D, which whose determinant it is equal to AD minus BC. So now again considering the matrix C, which is defined by A dash, B dash, C, D. So its determinant is A dash D minus B dash C. So now if you add these two, so B plus C, so you can see that AD plus A dash D minus BC minus B dash C, which is same as that of determinant of the matrix A. So here you can say that the determinant A, it is the combination of determinant B and determinant C. And now coming back to this, so here the same operation is been shown, and also here you can multiply the row elements by some constant scalar value. So here you can, we have shown the multiplication of the row 1 by the value T. So here we can write for the matrix B, we have considered as TA, TB, CD, which can be written as T into determinant of A, B, C, D. So now we have to remember some points in this property. The first one is we cannot add all the rows, only one row is allowed to change. So here as I told in the notebook I have shown that LHS is equal to RHS, that is determinant A value it is equal to the sum of determinants of B and C. That property we need to remember. And also matrix T into A, it has a factor T in every row. So here in this, we have shown the multiplication of the scalar value T with the first row. But when we write T into A, so this T is going to be multiplied with all the elements of all the rows in the matrix C. And for example, if you consider a volume of a box, and if all the sides are stretched by 4, then the volume is also going to be increased by the factor 4. So having that concept in mind, so we can apply the concept of T into A. So that is the third property. And the fourth property, if two rows of A are equal, obviously the determinant of such matrix will be equal to 0. So here in the first row we have AB, the second row also it will be having the same elements as that of the first row. So here you can see AB minus AB, it will be resulting in the value 0. So here it means, suppose if two rows of the matrix A are equal, then it will be, its determinant value it will be equal to 0. So here it is going to follow the rule number 2. So what is the rule number 2? So here the determinant it changes when the two rows are exchanged. So the here also you can make the sign, we can exchange the rows and you can see the value. But since it is resulting in the value 0, the sign doesn't matter in such cases. And the fifth property, so subtracting a multiple of one row from another row, it leaves the same determinant. That is, for example, if we consider the subtraction of one row of the matrix from another row, here it is shown as A minus LC and B minus LD. Suppose if you perform this operation, it will be resulting in the same determinant A, B, C. So here this property, all these properties, it can be usually verified whenever you will be solving the problem. And the sixth property is, suppose if the matrix A, it is having a row of zeros, then the determinant of A, it will be equal to 0. So here you can see one row, it consists of 0, 0. Second row is CD. So but when you calculate the determinant, its value, it will be equal to 0. So even it can be applied for any number of the square matrix. Even if you consider 3 cross 3 matrix, and in that case, if any one row is 0, then also the determinant of such matrix, it will be 0. And the remaining properties will cover in the next class. Thank you. You can wind up.